Nice game yesterday. Okay. Yesterday we finished talking a little bit about the fabrication and some of the circuits we have to develop to create the qubit and measure this kind of device. And today I'm going to talk a little bit about how we do the measurements to be sure that the qubit's alive and everything's there and is working properly. Okay, so after we prepare the sample, make the cavity, make the qubit, we need to start to do the first measurements to be sure that the sample is alive. Okay, everything's working the way we designed the sample. Okay, so the first thing we do, we put the sample in our refrigerator and prepare the measurement setup. And the first thing we are looking for is the cavity. We are going to see if our cavity is working properly. So we use this equipment here, or we can build one equipment like that. And this equipment is measuring the transmission through the cavity to see if my coplanar waveguide has the resonance frequency I was looking for. And for example, here in this measurement, I see here is around 5.89 gigahertz. And from that measurement, I also can have a first idea of what's the leak of photons I have in my cavity, the kappa I have here. That's the first measurement to be sure that everything's working correctly. Now I need to see if my qubit is alive. If I have a qubit there, and if the qubit is working properly. And for that, we do a second kind of measurement. Okay. First, when you are looking for the cavity, we send a lot of photons to the cavity to receive a lot of photons back, and then we can have an idea what's the behavior of the cavity with high power. Okay. Then, now that we know what's the resonance frequency of the cavity with high power, what we do, we start to reduce the power of, or the number of photons we are sending to the cavity. Why we do that? Because when we have a system now that's composed of qubit coupled to a cavity. Okay? When we have a lot of photons, the effect of the qubit in the cavity is really, really small. It doesn't really affect the cavity. So we have basically the bare frequency of the cavity here. But when we have a small number of photons arriving to the cavity starts to change the frequency of the cavity. We start to changing the characteristics of the cavity. So we start to reduce the power, like here is minus 60 dBm, for example, send the signal to the cavity to measure the cavity. When we do that, we are not measuring only the cavity now. We are measuring the rest state of this system qubit cavity. And we see a shift in frequency of the cavity. Okay? And this shift indicates to us that the qubit is alive. We have a qubit there, our processing worked well, and we have a qubit working. So what we do this kind of a measurement here. Okay? So this is a measurement of one cavity at high power, and then we start to reduce the power we are sending to the cavity. Okay? And you see, at high power, we have basically a peak here around 5.09 gigahertz. When we start to reduce the power, the peak starts to shift here and goes to 5.075 gigahertz. So this is the indication we are looking the first part of the experiment to see if my design worked and my fabrication worked well. You know, that's the kind of image we are looking for, and that's the kind of spectrum we are taking from the cavity. So now that we know that we have a qubit, we want to see if we can start to control the qubit. We can start to apply modify the frequency of the qubit to be sure that what's the frequency or what's the energy of this qubit in relation to the energy of the cavity. Okay. So, okay, this button is not working really well, but now it's done here. Okay. So now that we know that we have a qubit there, and we know the frequency of, or the energy of the cavity, we need to know what's the energy of the qubit. We need to have an idea what's the energy we have in the qubit. If you guys remember, when we did the qubit, we added there the two pads junctions here, the cavity coupled to the qubit, and then we came here and bring here a line near of the qubit that I can put in this line some current, can apply some voltage here, and then I can start to measure some current passing through here. When I have current passing here, I can induce a magnetic field, and I can modify the energy of the qubit. Okay? And we change this flux passing to the qubit and measure the frequency of the cavity to see how the cavity changes when it changes the energy of the qubit. When I bring the qubit near of the cavity, I will have a larger shift of the frequency of the cavity. When I bring the qubit far away from the cavity will not feel the qubit so much. So during that, we will see something similar with that here. Okay. On the x-axis here, I have a voltage here, okay, that in the end I can convert this to flux. But here you can see here this kind of behavior. And this behavior is what we expect to see when the qubit is coming near of the cavity and far away from the cavity when I change the flux passing to the qubit. Okay. So that's the second part. Now I know how I can change the flux in the qubit to bring the qubit near or far away from the cavity. With that, I can start to control the frequency or the energy of the qubit. Okay. So here's the intensity of the signal. You see here this sinusoidal form that is repeating, and that's when I change, increase more the flux, I start to have that behavior that goes with the cosine of the Josephson energy that I showed you guys yesterday. Okay. Now that I can start to control the qubit, I want to bring the qubit in some region that I expect to see the qubit there, and I want to excite the qubit to see the cavity change frequency. So what I mean with that? Remember I told you I have here the peak that represents the cavity. When is the ground state, I have this behavior. When excited state, for example, this is not the best color. Let me change here. Okay, have this behavior. So we are going to use this technique again to see what's happening with the qubit. Okay, so what we do now, we are going to send a second signal to the qubit to excite the qubit from the ground state to the excited state, and look the cavity. But now I can kind of control where the qubit will be. What's the energy of the qubit? Okay. So this is the kind of measurement we do there. We have the same setup to send signals to the cavity and get back the signal of the cavity. And then we fix in a specific frequency you want to measure. For example, this one here. That's the frequency we are looking the cavity. Okay? Then we start to change the frequency of a second tone that's produced in this setup here and send this signal to our cavity qubit circuit. When the frequency of this signal hits is the same frequency of the transition from ground to excited state of the qubit, I will have this shift happening, and then I will see a decrease in the intensity of the signal passing through the cavity. And this is what we will see when you do this kind of measurement. See nothing happening, and in some moment you see a dip, then come back, and goes up again. And this measurement gives us the idea, okay, now I know what's the frequency of my qubit for this specific flux I adjust in my setup. Okay. Something interesting also you can do something interesting here as well. If you put a lot of power here in the setup to excite the qubit, you also can excite the two-photon process to excite from the ground to the second excited state of the qubit. Have two processes, two-photon exciting from the ground to the second excited state of the qubit. Okay? And you see a second peak here. Okay? With that, now you have an idea what's the frequency of the second energy level of the qubit. With that, you can have an idea of how unharmonic is your qubit. You have an atom there. You need to be sure what's the energy levels you have inside to not excite transitions that you don't want. So this is a way to check that. Okay? Well, that's what we do here. We do these measurements, do some calibrations, and then you have this idea. Then we can change the flux and do this again and see this peak happening in other frequencies and have an idea of what's happening there. If we do this measurement with this setup here on all the time, that's not exactly what you see. Okay. Okay. So if you have the source here always on, when you do the measurement of this cavity, you'll see all the photons that are inside of the cavity, the state you have inside of the cavity. And you see something like that here. Many peaks that are related with the state you create inside of the cavity because of the signal you are sending to your harmonic oscillator. Okay? Here is a coherent state you have inside of your cavity. And also you can do the same thing for the two-photon process from ground to the second excited state of the qubit. Okay. Okay. So we are doing these measurements until now with the signal to measure the cavity always on. So we always have a lot of photons inside of the cavity. Then when we measure the qubit will fill all the photons inside of my harmonic oscillator, my cavity. And this could be a problem because we do some dephasing the qubit. You modify the behavior of the qubit in some ways that are more complicated to work with. So we wanted to make something that will facilitate our measurement or our math in the end. So what we need to do is to do a time domain measurement. Okay? We need to do the measurements with no photons inside of the cavity. And we do that creating pulses that we are going to send to the qubit and to the cavity in specific times to do the measurements we want. Okay? So we do something like that. I have here time. I'm going to send a signal for the qubit and cavity. Then for the qubit, I'm going to send I put something like that. And here the cavity. And I put some square pulse here. That this square pulse will define the time I'm going to send a signal to the qubit. And other sign, other square signal that I will choose to send the signal to measure the cavity. And the first thing, when this is on, I'm sending signal to the qubit. When it arrives here, the signal is turned off. Then I came and I turn on my signal to the cavity. And this way, when we send the signal to the qubit to excite, to do some operations in the qubit, I have no photons inside of the cavity. Or the photons I have there are only because of the temperature or some noise that came through the lines or for some other source that I don't know that in that moment. But it's not photons because I'm exciting the cavity. So the qubit will not feel any photon, basically, in that moment. So the qubit here, you change the behavior of my cavity, but will not be affected by the number of photons of the cavity. Then I send a signal to measure the cavity really fast, to not disturb the cavity enough to modify a lot the behavior of my qubit. Then I send the signal, and then measure the setup. So how we do that? We use this kind of device here. That's the people in electrical engineer use this a lot. You have a local oscillator here with a specific frequency you define that we are going to use. You adjust that. Then you use these two ports I and Q here that you modify the signal I'm sending here. And this port RF, you come out a signal that's proportional to the I and Q I'm putting here. Okay. Doing that, I can, for example, put a sine wave here with some frequency, adjust I and Q, and modify the signal I have in the output here. I also can change the phase of this signal controlling I and Q here. With that, I can start to think about make pulses in the X direction and the Y direction in the Bloch sphere. I can start to think about how can I do that kind of measurement there, and create these ports that are important for many experiments. Okay? So thinking about that, I can show you some ideas of how we do that. If you want to create a pi/2 pulse here, we send a signal here with a frequency of the qubit I want to use. Then I need to decide what's the time I will have to create a pi/2 pulse. This first pulse here is in the X direction. The first one, I decide to be X. I need to define one. First one, we decide that's the X. Then the next one I will create will be the Y. I need to define some time that I need to measure that will create to me a pi/2. Then I control the signals in I and Q port, send the signal to my qubit, and then I do this rotation I was waiting for. Or I can do a pi pulse here. It's the same idea. I send some signal that is the frequency of the qubit. I open to only let this small period here, small time, go to the qubit, then do this kind of transition here. Now that I know what's pi/2, I can think about to do a pi/2 in the Y direction. I do the same thing, but now instead of send the signal to the I port, I send the signal to the Q port. That you only change the phase of the signal I'm sending to the qubit. So the waveform that is, you move your qubit here, you'll be controlled by the phase of the electromagnetic wave you are sending inside of your system. So this is the way you change for X and Y there, okay? But there is a question that I didn't answer you yet. How I know what's this times here? Pi over 2, pi over 2 in the Y direction. How can I decide that? How can I know that this is the correct way? Okay. We need to do some kind of measurement to decide that, to be sure that this is the time that you do this kind of rotation in my qubit. Okay. So, coming back a little bit, how will you do the measurement of my cavity? Okay, using pulses now. I have a source here. Okay, I produce my signal here that is in the frequency of the cavity. I divide this signal in two parts. One part I keep at room temperature. The other part I send to my equipment that will create the pulse to do the measurement. Okay, this is the readout time here. I send the signal to this port. They create the pulse. I send this pulse to the cavity. I bring back this pulse. Then I do the other, I invert the process I did before. In the beginning, I send a signal in the I and Q ports and have some output in the RF ports. Here, I am doing the other way. I send a signal in the RF port. I have my original signal in the local port. And this device here, you compare both signals. Okay? And from that, we are going to get back the change in amplitude and the change in phase of the signal. This information of the change in amplitude and phase will be encoded in the IQ ports. I get this signal sent to the computer and do the calculation to get information about what's the change in the signal when the signal passed through the cavity. Okay. Okay, just to be, you guys have an idea. Here I have basically, each measurement will be something like 1 or 2 microseconds. I need to repeat this measurement like 100,000 or 1 million times. And I need to do this really fast to be sure that I can do that in a time that the student will be alive. And so the number of data that come out here is really huge. And I need to process this all the time to be sure that I have the statistics necessary to have information about what's the state of the qubit. So we have really fast computers and analog to digital converters that convert the signal from analog to digital to process the data and then convert this back to something that I can read. And most part of the software here we do in C or assembly to make the processing really fast. And then part of the processing we are trying to do using FPGA. So you need to know how to really do the processing really fast to have a lot of data coming out in a really short time. Oh, this is basically the idea here. Okay, all of this process here, there is a lot of other qubits that goes here in the middle because this is not ideal. This is not ideal, so there is a lot of details. Have resonances happening all the way around. You have the delay of the signal coming through this line and the signal going to this line here. You need to adjust all these delays. So now the speed of light inside of the cables is an important factor here. Okay? If one signal arrives or goes out in that time different than the one the side, this could be a problem. I could have photons inside of the cavity, or I could be exciting the qubit and measuring it at the same time. So we need to adjust all the times here, the length of the cables, adjust the phase that happens. The phase here inside of the cable can modify a little bit because of some characteristics of the cable, and all of that we need to adjust during the experiment. Okay, so we got all of that signal come out of the cavity. Now we need to convert this to something that we can read, we can work with. Okay? So you have our signal coming from the cryostat. You have our local oscillator, as I showed you before. So you have here the I and the Q signal come out, going to the computer. That I'm going to convert to analog signal to digital signal. And probably you'll see something like that here come out of your measurement setup. Okay? Then what you need to do, you need to convert this from analogical to digital. So you have a fast acquisition board that can get the data really fast and transform this in digital signal that can go to my computer and try to do some math on top of that. So when I have the signal here, I have the signal, the I and Q here, changing in time. This is the, I have the signal oscillating here. You can represent this as an oscillation in the I-Q plane here. Okay? Then we do a Fourier transform here. With the frequency, I decide to do this measurement here. And I do this, I have now a frequency, a signal that represents the changes in amplitude and phase of my signal. I integrate the signal for some time. That's this time here, the time I do the measurement. Repeat this measurement many times. And from that, I get information about the state of the qubit. Okay? So there is a lot of engineering problem happening in this part here to processing the data. There is also the physics you need to understand to be sure that what we are doing here really brings me back this information of the state of the qubit. But there's some papers and some books explain exactly why this processing here bring back the information of the qubit. Not any signal, you have no idea what's the meaning of that. Okay? So this is the idea. We call this analog demodulation. Here, data sampling. Here, we are. This is a DPS. That's basically we are doing here a homodyne digital conversion. We start with a heterodyne, then we convert to a homodyne conversion in this part of the process here. Now we understood a little bit about the elements we have inside of our system. Let's look a little bit about the measurements. Okay. So how will you do that? Okay. So we have here time and the signals I have in different parts of my system. Okay. Here is the source 1, source 2, the signals here. Here is the AWG that send the signal, the information to this part of the equipment that you create the pulses. The channel 1 here, you send this signal here to this part, that you send the signal here and bring back the signal and send to my digital, analog digital converter. And some other readout signal that going to my system and send the signal to my computer that can, I can get back the information about the state of the qubit in the end. So when I send this square pulse here from channel 1 here to this source 2, I'm only sending to my cavity qubit system this signal here. So this is exciting the qubit here. Because I already, I did the experiment before to be sure what's the frequency of the qubit. And then I have my readout signal that I know the frequency, and I have created this pulse here. I'm sending this signal here, then the signal here, and the signal is coming back here and going to the computer that creates this wave, these two waves that are interacting with my system. In the output, I have some modified signal from the original that I convert here to digital, and I get information about the amplitude and phase, for example, of my device. So when we do this measurement, what we do in the beginning is we fix this readout time here for some value that is enough to do a measurement of the cavity fast enough to have information about the state of the cavity, but not long enough to take a lot of measurement time. And we are going to change this time here, the time of the pulse I'm sending to excite the qubit. Okay? I'm sending, in the beginning, a really short pulse here to my system. So I have some photons arriving to my qubit, try to excite the qubit from the ground to excite the state. Then I'm keeping the signal a little longer to see if with that I change the qubit from the ground to excite the state. Then I start to increase this a little bit more to see if I can change the qubit from the ground to excite the state. And in the middle, you have the superposition of the both states. That's what we expect to see if we do the measurement. And that's basically what we will see here. So when you send the signal in the beginning, a really, really small pulse, you will not see the qubit going to the excited state. You not have enough energy to modify the qubit from the ground to excite. So we expect at the beginning you are in the ground state. Okay? We start to increase the length of your pulse. In some moment, you arrive here, where you are sure that you are in the excited state of your qubit. You put enough photons in the cavity to excite the qubit from the ground to the excited state. Then you keep increasing the size of this pulse and keep doing the measurement here. Okay? And with that, you got two informations from the data. First one, what's the time for a pi/2 pulse? And then what's the time you have for a pi pulse? So now, okay, now I know how to create a pi/2 and a pi pulse in my system. I can start to create the sports. I would need to do the measurements for more complex experiments. There's a lot of technical details here. For example, you are not really sure about what's the frequency of the qubit. You need to do a fine-tuning of the frequency. So we repeat this measurement for different frequencies near of the frequency of the qubit. Then we can get here where a region will have the maximum change in the excited and ground state for the qubit. And this gives you the information what's the frequency of the qubit for this measurement here. Okay? And here the measurement as a function of time of that. Here another measurement of that. The same thing here, you see the frequency around here. Okay? And now you did the first part. Now I have an idea what's the time of pi/2 and a pi pulse. Okay? The first time here I produce, I decide this will be my x pi/2. Okay? Then I'm going to invert the phase of my signal, and then I'll create my y pi/2 pulse. Okay? So that pi/2 that you guys put there on your math took us a lot of time to create here. Okay? I'm going to apply a pi pulse here. And this also gives you the information that you see, for example, in the IBM computer, when you have access to these computers. They do this kind of measurements, T1, T2, and this information generated with this kind of measurements, they have a protocol there, automatic protocol that get the qubit and do all these measurements for all the qubits to give you this information and do the calibration of what's a pi/2, a pi, and all of that, all of those ports you need to do the calculations. Because the qubit is interacting with the environment. If something changes in the environment, you see a change in these times here, and you need to correct for that. Okay. Okay. Now we have an idea of what's a pi/2 and what's a pi pulse. Now let's see if we can get some information about the quality of our qubit. To do that, first thing we measure is what we call a T1 measurement, that we're going to excite the qubit from the ground to excited state, wait some time, and measure the qubit to see if the qubit is still in the excited state. Okay? And so we have here our pi pulse here. We know the time. We send the pi pulse, wait some time, and then send a signal to measure the system. That we are measuring the cavity, not the qubit directly. We're measuring the cavity that you give us the information about the qubit. And we have this time here. That's what we have in this axis here. So when I send the pulse and measure the cavity, just after the pulse, I expect to see my qubit in the excited state, because I just sent the signal to create the excited state. Then, with time, I start to see the probability to find the qubit in the excited state to decrease with time. Think that each point here in this measurement is like 5,000, 10,000, or 1 million measurements of the same setup. We repeat for this time here a lot of times to have statistics enough to be sure this is the value we have there. So in this data here, then we fit this for some exponential decay. And for this qubit here, the T1 is around 14 microseconds. Okay? So this will start to give you the time, how many ports I can apply in my setup before I start to lose coherence and the quantum behavior I need to do the computation. Okay. Now we are going to do what we call a T2 measurement. Okay. And what we do here, we are going to apply a pi over 2 pulse that to put my qubit in a superposition state. Then we are going to wait some time, then apply again a pi over 2 pulse. Okay. So we are sending the qubit for the plane, xy, letting the qubit evolve some time, then apply again this pulse to invert 90 degrees, and then measuring again. So when they send the 2 pi over 2 pulse, one after the other, that's basically pi pulse. So what we expect in the beginning here is to see the qubit in the excited state. And that's what we see here. When we start to increase this time here, this t here, we start to see a change in the probability to find the qubit in the excited state. Okay? And if you do this with the frequency, exactly the frequency of the qubit, you see here the blue line. Okay? Because the frequency of the signal you are sending is rotating the same velocity of your qubit. So you see no change here. But if you modify a little bit the frequency of your signal to the frequency of resonance of your qubit, you see something like that here. And you can also fit this data and get the same information. Okay. Now you have the second information, the coherence time of your qubit. How long your qubit will be useful to do measurements that you need to be sure that this is long enough so you can apply all the gates you want, all the ports you want before your system loses the coherence. And again, when you do the measurement, you go to IBM or any other company and see this information, that's the kind of measurements they are doing there, to calibrate all the qubits inside of their device. The difference of frequency of the signal you are sending to excite the qubit and the resonance frequency of the qubit. Okay.
With respect to this T2 measurement, how much is the difference of this problem that you are like?
It's not a problem. It's just give you the information that both the qubit and the signal you are sending are not in the same frequency.
But how much contribution is because of problem of calibration with the
with that, we could do a fine-tuning of the frequency of your pulse to do the pi over 2 pulse. You can adjust it there. With this technique, you can use some techniques that you try, okay, I need to change a little bit frequency of my signal to excite the qubit a little bit to be sure that I'm not off of the resonance. Okay. Most part of the time, when you do these measurements, let me come back. It's really hard to really get here. This is 0.3 megahertz in 5 gigahertz. Okay, if the qubit, something happens, someone put a chair near of your setup, you see this change here. If you have a problem with the ground of your system, sometimes you see this kind of this stuff happening. That's why we need to calibrate your system all the time to be sure that everything is working the way you want. Okay. Now that we have the pi over 2 on the pi pulse, we need to be sure that we can create also the y pi over 2 pulse. And this is, we do that, change the way we send the signals in the IQ port here. We modify the signal we are sending to the I and the Q port, and this you change the phase of the wave I have here. I don't know if that's possible to see, but this light gray here has a shift in this region here of 90 degrees. Okay? And that's what we are going to use as a Y rotation of our qubit. Okay? Sending signals this way, you can start to control this. And this, you can do other rotations this way now. You see that if you start to control I and Q here, you can control the way you want to rotate your qubit inside of your system. You just need to know, okay, I'm here, I need to go there. How can I create the signals that goes here and here to move my qubit to this position? Okay. Then you can get some more optimization software, talk with some guys that work theory, and then they can help you to improve that and to optimize this kind of algorithm. And this is that you have. Now you have a way to create your pi over 2 pulse in the X direction. Now you have a port to create a pi over 2 in the Y direction. And then you have what we call readout X and readout Y, for example. You put these two together, and then you create the ports you want. Start to create the elements to create the ports to do the measurements. Okay. Until now, I just discussed with you guys, have one qubit and measuring one qubit. But we need 2 qubits to do something. Only one qubit, you cannot do a lot. But if you have a second qubit, a third, and more, you can do more interesting measurements. So what we do, we now have a cavity. One of the ways you get a cavity, and you put 2 qubits inside of that cavity. And you can use the cavity as a bus to couple both qubits together. So you create different qubits here. You put that in a cavity, and now your 2 atoms can interact through the cavity. Okay. And here's an example of a sample that has this kind of setup. Here and here are the mirrors or the capacitors that define my cavity. I put a qubit here, another qubit here, and I have my cavity here inside of my system. Here's the one example of the size of the qubit, 300 micrometers. Is around, I think, 50 or 100 micrometers here. So this is really huge. You can see with your naked eyes. Oh, talking about that. Okay. If someone wants to see, here is 2 samples with qubits inside. Okay. It's not useful anymore, but try not to open because then this will fly away and okay. So we have qubits inside of your cavity. Now you can start to play a little bit to see how can we create some kind of port that will couple these 2 qubits. Okay. So the first thing we do, we need to do all that measurements we did before. We need to find where if the qubit's alive, if the other qubit's alive, if when I change the flux through the qubits, what's happening with my qubits, what's the energy of the qubits. All of those measurements I need to do again, but now for the 2 qubits. And this is a measurement of the cavity. Here I'm measuring the cavity. And changing the flux, I'm sending for both qubits. In this way, I'm sending the same flux for both qubits. Okay, I'm modifying both qubits at the same time. Then I see this green line here. This is I'm changing the energy of the qubit. The energy of the qubit is increasing. Gets in resonance with the cavity. Then it goes up, and then comes down here. And goes up here again, and down here again. And now I have the same thing for the second qubit, the red one. The qubit's going up here, down, then goes up here again, down here, up here, down, up, down. Okay? So now you are modifying the energies of the 2 qubits, and then you can see the qubit getting in resonance with the cavity, and you are seeing how everything's going inside of your system. Okay? Okay. You see here, here the energy levels of the 2 qubits together. Okay, we start to have some more complicated structure here, but for example, you're only exciting 1 qubit. You can excite only this qubit here. You have the other energy levels here, and exciting just this first one here. You can bring both qubits in resonance. So you modify the energy of 2 qubits to bring the 2 qubits in resonance. Then they have the same frequency, same energy. You can swap energy between both. If you can control that, you can excite one and bring this qubit to swap the energy from one qubit to the other. And then you need to decide how long you need to wait to do that. So you need to know what's the coupling you have between the 2 qubits through the cavity. Then you can decouple both qubits again and do the measurements of your device. Okay? Oh, now what I'm going to explain to you guys now is the iSwap or square iSwap ports. Okay, how we do that? How we get 2 qubits and start to play with them to create these ports here. Okay, so we can do arbitrary movement in the 2 qubits here, or we can create what's called iSwap or square iSwap here. Okay, and everything is based in this Hamiltonian here. I think you guys already have learned about that and know everything's happening here. That's the last day, so. Yeah, that's what I thought, that all those details, the guys, you learned a little bit before that. Okay, so how can we do this port? Really make the control all the commands to make this port here. So you have a resonator. the 2 qubits here, the right and the left, the cavity here, and you have your, you send the signals to your sample. You can send signals to change the flux to the qubit 1. Here you can send signals to change the flux passing to the qubit 2. And you can get your signal back, send this to your room temperature setup to measure this device. That's basically what I told you in the beginning of the talk today. So how we do that in the measurement? What's happening to create this port? Okay. I have here qubit 1, qubit 2 here, okay? I apply a signal only to the qubit, for example, this left one here. I send a signal only to this qubit here. That's the upper one here. So I change the energy of this qubit, and I change the energy from this point here to this point here, because I want to bring this qubit in resonance with this qubit here, okay? So when I change the flux, I start to modify the energy of the qubit. Then I bring the qubit in resonance with the other qubit here. And I keep the qubit here for some time. I move here, keep here for some time. Then I bring back here. Then I bring back the qubit here again, keep for a longer time. Then I bring back here and measure the qubit. Then I get the qubit, bring here, keep for some longer time, and bring the qubit back here and measure the both qubits. I may repeat that for changing the period that the 2 qubits are in resonance to be have information of what's the state of the 2 qubits after the interaction time here. Okay. So this here is the flux, is this flux here. I put first in this flux here, then I put in this flux, change the time. Put in this flux, change the time. Put in this flux, change the time. And do that until from this region of flux here. So here you see the flux, the time you keep the flux in some specific region. And here you are exciting the one of the qubits here, okay? Excite one qubit here, excite the other, and we are seeing the swap between both qubits, okay? And what you see when we are in this region here, that the region both qubits are in resonance, you see this graphic here. Is the probability to find the qubit in the excited state in the end. Oh, this time you have here is giving you the time to do the operation you decide to do, the I swap or square I swap or an angle you decide to put here. So this is how you create this port. And this port you can use to start to think now, how can I entangle both qubits? How can I swap the state of both qubits, create state in one qubit, send it to the other qubit? Do all this changing the flux in this way. Okay. And here is the probability to find the first thing grounded, the second excited, or the first in the grounded, the second excited, how this changes with time. Okay. Also, you can adjust this value here. What's the flux you need here, or the energy you need to put the qubit, and the time to really have the maximum probability to do the protocol you want. Okay, so let's play a little bit here what we can do with your system. You can apply pi pulse in the y direction, in the left qubit here. Wait some time, apply all other pi pulse in the same qubit. The same time you waited for your flux to work, okay? But we are not changing the energy of the qubit, just applying the 2 pulses and measuring the system. Because you need to be sure that we are not putting the qubits interaction and then bring it back, and it's not happening. They're not exchanging any energy. You need to be sure that that's what you are doing, okay? So we do the experiment without modify the energy of the qubits. And then we do the same thing. We get the left one, apply a pi pulse, get the right one, wait some time, then go to the right, apply a pi pulse, and then measure both qubits. When you do that, you have here this curve here indicating what's the energy of the both systems, both qubits in the end. Then you are going to repeat the same thing again, okay? We are going to apply a pi pulse in the left qubit, apply a full flux pulse on the qubit you want to bring in resonance with the other qubit. Then you are going to apply again a pi pulse in that qubit. So you put an excited state, then apply a pulse, put it in the ground state again, and measure the system. Then you do again the other measurements that you apply the pulse in the left qubit, apply a pulse to change the energy of your qubit, bring both in resonances, apply a pulse in the second qubit, and then measure both systems. Okay, A here, that's this setup here. Both pi pulses apply to the same qubit, the left one. You see this response here. That's the state of the qubit is almost not change with time. Okay, after 80 nanoseconds, you see both qubits going ground here, then up again. B here is this case here. You excite the qubit, excite the other qubit, wait some time and measure, and see no change in the state of the qubit. Only here, when you apply the pulse in the end, you see a modification of the states of the two qubits. Okay? But now we have this case here, where you put both qubits in resonance for some time. You really apply a pulse, bring both qubits together, tap the qubits interacting for some time. Then you see here in C, that's this case here. The probability to find one qubit to the other in excited state is changed with time. Then after your protocol, you can measure your device, okay? And here for the case, the other way around, because here we're applying a pi pulse in the left and in the right, and you see how this is modifying your device again. When you do that, you can get what's the duration of this flux pulse here to really put both qubits in the ground state, first in the excited, second in the ground, or the first in the ground, second in the excited, or both qubits in the excited state. So there's a way to be sure that when you bring both qubits in to interact, you really did a swap between the states of the qubits. Okay? Oh, with this port here, now you have the elements necessary to start to make interesting ports. For example, C0 port is based on that here. You can use this setup to start to create these more complex ports that are really necessary to make quantum computation in this kind of devices. Okay? Oh, see, this is 2010. This kind of 13 years. So that's was developed for 2 qubits this period, and today they can make this in more than 400 qubits at the same time. And that moment you will start to see the electronics you need to control all of those qubits together in a setup that all of them you do what you want is start to really get complex. You'll see that some of this, you have your qubits something like this size. The control room is basically like 3 or 4 racks of electronics. And all of that electronics need to be controlled really fast with really out of precision. And you need to calibrate all your qubits all the time to be sure that when you apply the pulses, you are doing that correctly. Okay. Okay. coming back a little bit, that sample stay in a dilution fridge like that one here. So you put your sample in some place like here, okay? And then have all the stages connecting, all the cables that control your qubit outside, bring lines to your sample here. When you have 1, 2 qubits, have a small number of lines here. When you start to have more and more qubits, this start to become a problem, because basically you have this stage here, 10 milli-K, that stage 100 milli-K. When you put one line connecting this stage with that stage, you are basically connecting a hot band with a cold one. You have something hot, something cold, you are connecting both with some cable. Some heat will start to flow to that cable. When you have small cables, you can calculate this here. Everything's okay, no problem at all. You can work with that. But when you have 400 qubits, imagine that you have to put 400 lines inside here. You start to have something big. And when you have something with a big area and connecting two stages here, you have a lot of heating coming through those lines. And this is a really big problem the guys had in the beginning, and they still have this problem. How can you keep the temperature of your sample cold enough to not have thermal excitations and modifying the state of your qubit? Okay. So,
For each qubit, you must have a line connecting.
Not today. Now they are doing some other techniques to prevent that. They're trying to decrease, but you still need 400. You need a lot of lines, because you cannot put all the signals inside of the bandwidth of your circuit. It's not only a problem of the I can put one line and have some bandwidth. I put all the signals I want inside of the one line only. But when I have 500, 1 million qubits, this is a nightmare. Because how can you, your cell phone, when you have a lot of people trying to talk at the same time someplace, you cannot have a call. And what they do there, they are doing frequency time domain, a division of the signal of the tower. So each one of us get a small frequency inside of the bandwidth of the tower on the street. Okay, so if there's a small number of people, everything's okay. You have your band there, you can use it without problem. When we have more people, you have subdivided that frequency in very small frequencies. And this starts to get a problem. And that's why you go to some soccer game or other place, and you get your phone, you cannot talk with anyone. Okay? And that's one of the techniques the guys use here. They use this frequency division technique to apply many signals in the same line and then send this to the other qubits. But you have a limit to do that. I think the largest one I saw was 500 megahertz. But I think the guys are trying to do 1 gigahertz of bandwidth for this device. So you have more band, you can put more information inside of the signals and send all of that to your samples. Okay? And also, some that I didn't put here, but you also need a second amplifier after the signal comes out of your sample. You need some kind of amplifier here that is quantum limited, that will increase the number of photons coming out of your cavity. You amplify this signal a little bit, some 20, 30 dB. Then the signal will go up to the second amplifier here, and that will amplify like 40 dBs. That will be enough to be above the thermal noise you have at 300 Kelvin. So that's one of the works we are doing in the lab now. We are trying to build one parametric amplifier, quantum parametric amplifier. To when we get the signal coming out of our sample, we can amplify that and send this signal to room temperature with high enough that the time of measurement I will have here is fast enough that I don't need to repeat the measurement like 1 billion times before I have some information about what's happening inside of my device. So all these statistics here are really important to understand what's happening inside of the device, okay? So one of the problems is that the energy of a microwave signal is really small. So it's really hard to develop an amplifier, to develop a single photon detector for this kind of microwave. So it's really small energy. So it's really hard to detect and tell to the computer, okay, 1 photon just got on your detector. So you need to detect that, and there is a lot of people working on that. Okay. Here's some information about how many equipments we need inside a fridge like that here. Okay, we have this single electron amplifier. That's a cryogenic amplifier here. They're connected to the 4K plate. They have they add something like 10 or 20 photons to each photon that arrives to the detector. So they add some noise to your signal. That's why we need a second amplifier at milli-K temperature to increase the signal above the noise. You need the cryogenic isolators. That basically this device, what they do, they allow you to send the signal in one direction, and when they send the signal in the other direction, they send the signal to some bath that you dissipated the signal. So this is like a diode for this kind of devices. The problem is that these cryogenic isolators, they need magnetic field. And magnetic fields can modify the energies of your qubits. Okay? Magnetic field is a problem so big that we need to get all the connectors, all the pieces we have demagnetize all of them before we start any measurement here. So we come back to physics 3, I think, that we basically make a coil, put AC signal, decrease it with time, put our device inside, and then we start to demagnetize the sample to see if we don't have any magnetic impurity interacting with our qubit. Superconductor lines that goes from here to here. These superconductor lines are really good because they have really low loss. We have copper nickel lines that are much more cheap than this one here. These are really expensive. It's really hard to work with because you cannot make welds in this kind of connector here. We have low frequency cables because you have all the noise at room temperature. My cell phone that has some like 5 gigahertz signal arriving all the time to my cell phone. Some of this signal is picked up by this system here, by the lines, and then this signal is coming to my sample here. So I need isolated from that as well. So I need lines that will cut this signal from my system. We have also these twisted pair lines. I think you guys, I don't know if you guys know, but basically we have get two wires, and then we twisted both wires, and then we do that when we have some signal, the same signal in both sides of the signal. They interact in out of phase, and then you start to attenuate the signal. And you see, each one here is a different material. Each one of the materials has a different property that will give me different characteristics that could help me to do the measurement. So solid state and properties of materials are really important to understand what's happening here inside. So that's one of the reasons I told you guys that we need to know everything we learn in our undergrad course. Okay. Also, we have in this system here 8 Tesla solar magnet that we can put a sample inside that we can put the sample at 10 milli-K and put on top of this sample 8 Tesla of magnetic field. So we could do measurements in this kind of setup if necessary. And a mu metal shield, that's basically a material that has the property to absorb magnetic field. So to isolate our sample from the universe outside. If a bus or a truck or a car drive around, you see changes in the magnetic field. This can affect the energies of your qubit. Okay. And more cables. You see, to do a project to put all of that takes a lot of time because there's really a lot of details you need to know to control. And here are fast acquisition boards, RF sources, lockings, isolated DC source, because I want to isolate electrically my qubit from the rest of the world. Okay, you see here, see this black line around here, my system, because this setup here is on a 15-ton concrete block that's sit on sand, sit on the floor that's isolated from the rest of the building. Okay, so this is to isolate this system from the rest of the building. And you see here these beams here. These beams are holding all the parts on the top to try to reduce any noise that that can come from the lines here to my setup as well. Also, I don't have any direct connection from the rest of my lab with this circuit here. So this is electrically isolated from the rest of the system. Okay. So we have also a ground that's specific for this system that's in the middle of the lab that's connected from the rest of the building. So if I need to ground this system here, I can ground in a ground that's not connected to any other machine. Okay? Because we saw before, if we share the ground, one guy in the other building turn on some machine and you see some noise on your system. And you start to go like crazy around the building. I ask if someone turned a machine that you didn't knew before. Guy turned a machine once a year, and that moment you turn on everything. Okay, something's here that wasn't here before. And then you get crazy trying to understand why it is that. And here, spectral analyzer, network analyzer. Here's our clock. We have an atomic clock in the lab as well, to rubidium clock to synchronize all documents, because they need to, everyone needs to have the same clock to create the signals. Okay, so again, all of that. Amplifiers, oscilloscopes, and IQ mixers, room temperature amplifiers, attenuators, coaxial cables. Like, I think I bought like 100 different coaxial cables, and I almost use all of them already, because I have cables connecting everywhere to connect all the machines. And when you go to IBM, the guy had someone just to create a new box that all that cables goes inside some place. You don't have to worry about that. Okay. And here an example of a sample here with the qubit in the middle. This is in this aluminum box, the junction in the middle. And then this is a kind of old sample, but you can see here, these are SMA connectors with the cables coming out here. This sample in the middle here. This is the 10 milli-K plate. We connected this here. Then we can close the system and start to do the measurements we need. And again, here, an example of the bridge we make to create the Josephson junction. Okay, and here's the document that we use to make the Josephson junction. Okay, here on this part here in red is that control the angle I do the position of the aluminum. Okay, I can adjust this part of the machine here. I can control the angle of this sample in relation to this pocket here. Here is the pocket where I put the aluminum. Then, and this hole here is the place we have the filament that we're passing current through the filament. Have some electrons come out of the filament. We have magnetic and electrical fields around here that control the electrons to arrive on this pocket here. We excited, we heat the aluminum here. The aluminum starts to evaporate because I don't have any atmosphere here. I am working with 10⁻10 torr inside. The atoms start to fly away from this source here, and then my sample is someplace here on top. With the sample here, I can adjust the angle and do the position to create the superconductor, the barrier, and the superconductor again. And again, I have a computer to control. I have many other equipments together here to really make some processing before I do the qubit. Because any oxide, any dirt I have in my sample, you destroy the characteristics of the superconductivity I have in my device, and this can be a problem. And there is some people that only work trying to develop new recipes and new ways to make a better sample here. Okay. Oh, okay. 2 minutes to 10:45. I think you. No. Okay. So I'd like to thank you everything, all the foundations that help us in some way, PESP, CAPS, NPK, and the groups that we work with to make the samples, CBPF, CTI, and also CBPF that help us there. Now we have some help from Sirius, and Peng is helping us to build the samples as well. And UNICT, CNPq, FAPESP. And here the image of to describe the lab. I tried to make some that could be what's the correct way to see this. That's the idea, to try to show someone what could be a superposition in some way. Okay? Thank you, guys. Questions? Okay, no questions. No questions. You can, we can go to the coffee now.
No, that is the closing remarks.
Before the coffee?
No, I'll do.
Okay.
Obrigado.
Nada.